Hello guys, welcome back to my YouTube channel. This is Bhagyalakshmi. Today we are going to study about 2D pipeline, 3D pipeline, RGB color model and CMY color model. The contents to be covered in today's video are 2D weaving pipeline, 3D weaving pipeline, RGB color model and CMY color model. First, let's see what's 2D weaving pipeline. The 2D weaving pipeline refers to the process of transforming and rendering a two-dimensional scene onto a display or image. Unlike the 3D weaving pipeline, the 2D pipeline doesn't involve the depth and perspective transformations since it deals with flat, two-dimensional graphics. Here, this is a block diagram of two-dimensional weaving transformation pipeline. So here MC is modeling coordinates, WC is world coordinates, VC is viewing coordinates, NC is normalized coordinates, and DC is DC coordinates. So here using modeling coordinate transformations, we construct world coordinate scene. Here we have constructed it and then we convert world coordinates to viewing coordinates. So here we have converted the world coordinates into weaving coordinates, and then we need to transform weaving coordinates to normalized coordinates. Here it is, and then we need to map these normalized coordinates to device coordinates, and hence we get here. These are the following steps involved in the 2D weaving pipeline. So the first one is modeling. It is similar to the 3D pipeline. The modeling stage involves defining the 2D geometry and objects that make up the scene. This includes specifying points, lines, curves, and polygons that constitute the graphical elements. Then weaving transformation. In the 2D pipeline, the weaving transformation is relatively simple and typically involves translating and scaling the entire scene to fit within the desired viewport or window on the display. It determines the position and size of the 2D scene in relation to the output device. Clipping. Clipping in the 2D pipeline involves removing any graphical elements that lie outside the viewing window or viewport. This process ensures that only the relevant portion of the scene is displayed, improving performance and efficiency. Rasterization. Rasterization converts the vector-based geometry into a raster image format suitable for display on a screen. It involves determining which pixels in the 2D image correspond to the geometric primitives such as points, lines, and polygons from the 2D scene. Determination. The visibility determination step checks whether a pixel should be displayed or hidden based on its position and depth. Since the 2D pipeline doesn't have depth information, this step is often straightforward and all the pixels within the viewing window are considered visible. Shading and coloring. Shading and coloring calculations determine the final color and intensity of each pixel. Techniques such as flat shading, Choroid shading or Phong shading can be applied to achieve different lighting effects. Additionally, color or texture information can be applied to the graphical elements to enhance their appearance. Pixel operations. Once the final color of each pixel is determined, additional operations such as blending, anti-aliasing, and post-processing effects can be applied to improve the quality and visuality of the rendered image. Display. The final step involves displaying the rendered 2D image on a screen or output device, resulting in the visualization of the 2D scene. The 2D viewing pipeline is generally simpler compared to its 3D counterpart since it doesn't involve the complex transformations associated with perspective and depth. However, specific implementations and optimizations can still vary depending on the graphics library or rendering framework being used. 3D weaving pipeline. The 3D weaving pipeline refers to the series of transformations and steps involved in rendering a three-dimensional scene onto a two-dimensional display or image. The pipeline encompasses several stages, each responsible for different aspects of the rendering process. Here in the given figure, we can see the general 3D weaving pipeline where the modeling coordinates, world coordinates, weaving coordinates, projection coordinates, normalized coordinates, and device coordinates are used. Where the uh, transformation is used like modeling transformation, weaving transformation, projection transformation, normalization transformation, and clipping, then viewport transformation. So this is the general 3D viewing pipeline. These are the steps involved in the 3D viewing pipeline modeling. This stage involves defining the 3D geometry and objects that make up the scene. It includes specifying vertices, edges, and faces, as well as their positions, orientations, and sizes. Viewing or camera transformation. The viewing transformation defines the position and orientation of a virtual camera in the scene. It determines the viewpoint from which the scene will be observed. The camera transformation moves and rotates the entire scene to align it with the camera's viewpoint. Projection. Projection transforms the 3D scene into a 2D representation by mapping the 3D coordinates onto a 2D plane. The most common projection techniques are perspective projection, which mimics the way human vision works, and orthographic projection, which preserves parallel lines. Clipping. Clipping involves removing any parts of the scene that lie outside the viewing volume defined by the camera's frustum. Objects or portions of objects that are not within the viewing volume are discarded. That is nothing but clipping. Rasterization. Rasterization converts the vector-based geometry into a raster image format suitable for display on the screen. It involves determining which pixels in the 2D image correspond to the geometric primitives, such as points, lines, and polygons from the 3D scene. The next step is the visibility determination. In this stage, the visibility of objects or parts of objects is determined to decide which pixels should be rendered. Techniques such as Z buffering or depth buffering are commonly used to keep track of the depth of each pixel and determine the visibility of surfaces. Shading and lightning. Shading and lightning calculations determines how light interacts with the surfaces in the scene, giving the objects a more realistic appearance. Various algorithms are used to calculate surface normals, lighting models, and material properties to determine the final color and intensity of each pixel. Texturing. Texturing involves applying 2D images onto the surfaces of 3D objects to enhance their visual appearance. Pixel operations. Onto the final color of each pixel is determined. Additional operations such as blending, anti-aliasing, and post-processing effects can be applied to improve the overall quality of the rendered image. Display. This is the final step. It's important to note that the specific implementation of the 3D viewing pipeline may vary depending on the graphics library or rendering framework being used. Additionally, optimizations and advanced techniques can be employed at each stage to improve rendering performance and achieve more realistic and visually appealing results. Next, we see the RGB color model. The RGB color model is a widely used color model in computer graphics and visualization. It is an additive color model that represents colors by combining various intensities of red, green, and blue light. In this model, the three primary colors RGB, that is red, green, and blue, are mixed together in different proportions to create a wide range of colors. The RGB color model is based on the principle that when red, green, and blue light are combined at full intensity, they produce white light, while absence of all three components results in black. In the RGB color model, each color channel is represented by an 8-bit value ranging from 0 to 255, which corresponds to the intensity of that particular color. By varying the intensity of each channel, any color within the RGB color space can be created. For example, we can see the below given examples. Here we can see the color model of RGB where red, green, and blue colors are used as primary colors, and all the other colors are obtained by them. And when three of them are in equal intensity, when three of them are having equal intensity, we obtain the white color, and absence of them results in the black color, which we can see in the figure. The RGB color model is widely supported by various software applications. operating systems and image file formats. The RGB color model forms the foundation for many other color models, such as this CMY model and HSL or HSV model, which is used for color manipulation and adjustment. CMY color model, also known as the subtractive color model, is particularly used in printing and mixing physical pigments. CMY stands for cyan, magenta, and yellow, which are the primary colors in this model. The CMY model is based on the principle that each color absorbs or subtracts certain wavelengths of light, resulting in the perceived color. In the CMY color model, colors are created by subtracting specific amounts of cyan, magenta, and yellow pigments from white light. The absence of all three pigment results in white, while the presence of all three in full strength produces black, which is totally opposite as we have saw just now in the RGB color model. Then the primary colors in the CMY color model are defined as follows: cyan, magenta, and yellow. Cyan absorbs red light, reflects green and blue light, whereas magenta absorbs green light and reflects red and blue light. Yellow absorbs blue light, reflects red and green light. This is the representation of the CMY color model we can see here in the below given figure. The CMY color model is widely used in printing, where it is employed as the basis for subtractive color mixing. In printing processes, cyan, magenta, yellow, and sometimes black, which is represented as K, inks are used to reproduce a wide range of colors by selectively subtracting light wavelengths. The addition of a black ink component, Cmyk color model, which is again renamed, is necessary to improve color accuracy and achieve a wider color in printing. It's important to note that the CMY model is not a perfect representation of color, as it does not include all visible light wavelengths. Therefore, other color models such as RGB may be used for more accurate presentation and manipulation in computer graphics and visualization. Thank you.